Hello, my name is Stephen Smith. I'm at Boston University and I'm going to talk to you about mesospheric bores, their global and seasonal occurrence. The observations were made using a series of all sky images that record nighttime airglow. These airglow layers reside at about 100 kilometers. There's several of them. There's one, green line oxygen, which is at 97 kilometers, molecular oxygen, which is at 94, neutral sodium, which is at 90 kilometers, and hydroxyl, or OH, which is at 87 kilometers. And there's a schematic diagram there to show you the heights, the relative heights. On the bottom left, you can see a photograph from the International Space Station showing these airglow layers. You can see the broad red line atomic oxygen layer at 250 kilometers in the F region. And then below that, you can see a thin green line, which is the green line due to atomic oxygen in the upper mesosphere, and also a sodium. You can see the neutral sodium layer as well. Here's a view of the green line from the ground. You can see the green line oxygen there. This is an all sky image. The zenith is right in the center of each image, and the horizon is around the edge. Now, in the atmosphere, temperature generally decreases with altitude. Any region where the temperature increases with altitude is called a temperature inversion layer, and that's usually a region of hydrodynamic stability. Now, inversion layers are a common feature in the upper mesosphere, and they're usually a few kilometers thick. And you can see at the right there, this is a SABRE measurement showing an inversion layer between 90 and 94 kilometers. It's 40 Kelvin inversion. These layers tend to cause gravity waves to become trapped or ducted within the layer. So what are mesospheric bores? Bores are a non-linear type of ducted gravity wave. They have a frontal onset of either enhanced or depleted airglow emission, followed by a train of waves or a train of turbulence. They require a ducting region, like an inversion layer or a wind shear, and they can propagate only horizontally. They have large amplitudes and very little attenuation, so they can propagate very large distances, hundreds of kilometers, sometimes over 1,000 kilometers. They also exhibit sometimes brightness complementarity between the emission airglow layers. You can see that in this image above. You can see bright OH airglow moving downwards into a dark region, and the green line on the right is a dark bore moving into bright airglow. They have very typical speeds and scale sizes compared to normal gravity waves, as you can see. Now, here's a schematic of how a bore propagates. You've got a temperature inversion layer in A, and that creates a ducting region, sort of as seen in figure B. I've put the airglow layers roughly where they reside. And then you have in figure C, you have a bore propagating to the left. And you can see, if you notice, that the phase at the top and the bottom of the duct are 180 degrees out of phase. And that's how that brightness complementarity occurs. Now, here are some videos showing a bore disturbance. This was over Texas a few years ago. And you can see a very large, extensive train of waves moving southwards. This is in atomic oxygen. And it's the same image, but in black and white, has been unwarped and mapped down onto the ground. And you can see this same bore moving pretty much southwards over McDonald Observatory. This was also visible to the naked eye. Okay, this image on the left shows this complementarity. You can see a bright green line bore and a dark hydroxyl bore moving together. And then on the right-hand side, this is a time evolution of that Texas bore. Time is going upwards, and it's moving towards the left. You can see how waves are being generated off the back of the bore as it moves leftwards, as it dissipates its energy. Okay, Boston University has a large network of images around the world, and here's a map of them. We have about 12 locations around the world, and these consist of a BSCCD camera with a fisheye lens and a filter wheel. And each are in various geographic locations. Some have unique gravity wave sources. Some are mountainous, some are oceanic, some are more continental. I looked at 3 of these sites. One was at McDonald Observatory in Texas. This is a continental, I call it a continental system. The gravity waves generally originate from weather systems and the jet stream. The second site is at Arecibo Observatory. It tends to be just gravity wave sources like weather systems. And then the third site is Ionosphere in Argentina, in the southern hemisphere. That's a mountainous site in the Andes, in the foothills of the Andes. There's a lot of waves generated there in the mesosphere that propagate up to the mesosphere due to orographic forcing, but there are also some weather systems as well. And so I took bore measurements from this site from the year 2015 and analysed those. That's what I've done so far. And here are some of the results. McDonald in the black, Arecibo in the red, and Ionosphere in the blue. You can see there's roughly about 6 to 8 events per month, and this included many faint events. They're more common than expected from what's been previously published for mid-latitude bores, which is usually about 2 to 3. The naked eye events were quite rare. Seasonal occurrence, they were pretty similar, but the McDonald Observatory had a very strong winter maximum, whereas the the Arecibo had dropped right off during the winter. Otherwise, are pretty similar. Here is the directions of the bores from McDonald, Arecibo, and Ionosphere, and you can see that the McDonald Observatory directions are much more variable, but they have a higher recurrence. There's much more of them. There's about 100 bores there in 2015. Arecibo and Ionosphere had a much more consistent directions. Arecibo was more equatorward during the spring and the summer and poleward in the winter. And Ionosphere was mainly northwest and poleward in the summer. These directions reflect the changing filtering within the prevailing winds in the stratosphere and the mesosphere, and also in the changes in sources with season. Here is the time of zenith transit of the bores over each of the sites. And you can see that they're all pretty consistent, and that the average occurs roughly about 1 or 2 hours after local midnight at each site, and that's quite consistent. That suggests there is some sort of tidal influence in their occurrence, because the tides at that height, whether they be semi-diurnal or diurnal, tend to be relatively stable over days. The lifetime of the events were also about, on average, 3 hours. There were some longer than that, and that could be due to selection effects due to the observation times, but they were quite consistent, as you can see. There was quite a few multiple bores for each night. In other words, more than one bore a night, and between 15% and 25% of the cases there were multiple bores. And what these seem to be, they seem to be related in the sense that they were in the same field of view usually, had the same phase speed, and also the same directions. And so, if you looked at it as a movie, it looks like a surging behaviour, and which suggests that they all have the same source. There's only a few that have different propagation times and directions. Another interesting thing was consecutively nightly occurrence. Bores occurred on consecutive nights at the rate of 20 to 30% of the time, and that rate's probably higher. There were some nights where the next night after that, also had bores, but the weather conditions on the consecutive night wasn't good, so you couldn't see. So in most cases, they had similar local times for the zenith crossings, and they also had similar velocities. And that's probably associated with a diurnal tidal wind structure, because that is a stable feature in the upper mesosphere over several days. So temperature inversions are commonplace in the upper mesosphere, and bores are less so, only about 6 per month, 6 to 8 per month. So we can assume that there are suitable ducting conditions already in place, and so really, for a bore to occur, you really need the background wind field to dictate when it can occur or not, in terms of its filtering from lower down and critical layers below. So that 20 to 30% bore occurrence rate suggests, in consecutive nights, suggests that a diurnal or semi-diurnal tidal influence is influencing the occurrence times or the origin. So in summary, mid-latitude mesospheric bore occurrence is more common than expected previously. It's about 6 or 8 per month. McDonald, I looked at McDonald and 2 other sites during 2015 as a pilot exercise. McDonald had a higher occurrence compared to Arecibo and Ionosphere-thermosphere, which exhibited similar rates, but there were large differences during the winter, and that's maybe down to just weather. You just didn't see them because of the cloud. On consecutive nights, there was a 20 to 30% nightly occurrence, which is consistent, and also consistent zenith times, which suggests strongly that it's a tidal influence on occurrence of bores. In terms of regional differences, the McDonald observatory, which is a more continental type of region, had much more variable occurrence, but it had a higher rate of occurrence. Arecibo is oceanic, and so it was consistently more equatorward during the spring and the summer, and the mountainous site at Ionosphere was mostly towards the northwest and poleward in the summer. So much more consistent. The next things I'm going to be looking at is characterizing the amplitudes of the bores and the phase speeds, analyze more of the years. There are 5 years to look at in total. There are also 5 other sites. Also incorporate more of the CEDAR data to look at the existence of inversion layers and characterize those. Investigate tidal variations is an important one, and then after that, try and investigate the source candidates for these bores. So thank you.